Hi everyone, are you able to hear me and see the screen clearly? All right, so this is 4th March and for ML. All right, so there is a question from Binta that there is no text for the topic 6 to 10. Could you confirm when they will be available for us to practice in CloudX Lab? Which text as in, okay, which text are we talking about, Binta? You mean this text here? The text here you're talking about? Habinta, are you able to hear me? So my question is, which text are you talking about in this? Inside this training? Because here, I don't think we'll be putting text anytime soon. Okay. We have not prepared the text for here. Okay. We might be putting maybe exercises in these projects. Okay. We'll be putting more exercises in these, like the way we have kept it here. Okay. Like this, we'll be putting more exercises, but we won't be putting text anytime soon. Here also, right now, there are no exercises, so we'll be putting more exercises here. Okay. Okay. So yes, we'll be adding more exercises to it. I think that's what you mean. Okay. We'll be putting soon. Okay. Some of the, I think the training models, I think the exercises are created. This week we'll be importing adding the exercises to this one. Okay. All right. Question. So this we will do on next Saturday. So next Saturday we will give you a brief overview of the tutorial. All right. And then, okay, to the topics of, okay. All right, so should we start? And next Saturday, yeah, the extra topics we talked about, the topics like XGBoost and time series, and if time permits, we'll talk about naive Bayes. Okay, and so on. All right. So that's the plan for next Saturday. And next Sunday, we are starting with deep learning. We'll be starting with TensorFlow in next session. So that's what is the plan. All right, so let's start for today. So one thing that we were discussing is that we should take projection. Projection is like taking a photo, right? Or throwing a light, and uh, basically when we throw a light on something and see the shadow, that's basically what do you say? Basically, when you throw a light and look at the shadow, that's basically converting a 3D object into 2D object. Similarly, taking a photo also means converting 3D object into 2D object. So you generally take photo, or you uh, l- look at the shadow from the angle where there is a maximum variance. Okay, so what does it mean by variance? Variance means the distance from the mean, the square of the distances from the mean, and if you sum that up, that will be the variance. So if there is a data set that is varying too much, that will have more variance as compared to the data set that is varying too less. Okay, so let me ask you in a simple way that if you have a data set something like 1, 2, 3, 4, okay, and 1, 3, 5, 7. Which one will have more variance? This is say A, and this is say B. Okay, so A will have more variance than B, or B will have more variance? Which one out of A will have more variance? Okay, the way we compute is we compute the mean. Okay, we say sum of okay, how should I say A? In terms of numpy, what will we do? We'll say A minus mean of A, right? And we square it, right? We square it, and then we sum it. Okay, so this is what it means by variance. Okay, so yes, so B will have more variance. That's correct. And yes, describe the variance is so useful and so common that we have functions in every language, starting with R, starting with, and even in NumPy, we do have, in pandas, we do have the methods to just compute the variance. Thank you, Noor. All right. Now, so here the distances from the mean is varying more in case of B as compared to A. All right. In all of these, so the mean of this will be 2.5, and the distance of all will be 1.5, correct? While in this case, the 4 will be the mean, right? And distance of each one is going to be 3, correct? So the square of 3, and if you sum it up, then you will get the variance. Okay. So this one is going to be how much? 1 minus 4, right? So 3 square is 9 plus 9 plus 9 plus 9. So this is the variance in this case. Okay. And right. I think in variance, do we need to divide by n? That's in case of mean error or right? Do we divide by n? I doubt. Let me just check. In variance, you don't divide by n, right? Or you divide? Hmm. See? So basically it's the summation of okay. Or is there a better page which could just quickly show? I doubt if we divide by n. We do divide by n, you're right. Okay, we do divide by n. Thank you. All right. So yeah, but that doesn't matter. So whether you divide by n or not, it'll remain mostly the impact will be more with respect to the numerator because that one has the square. Okay. So yes. So we do divide by n. Thank you, Noor and Bintao and Gopi. All right. So yes, so we do divide by n. So in both the cases, it is going to be 4, right? And here it is going to be 1.5 square, that is 2.25 plus 4 times. So you can see. Okay. So I hope this is clear. So this is the variance in both the cases. So you can see clearly that the variance in case of B is really high, right? Now, so in the same way, in the same way, so theoretically, variance represents how much varying is the data set, right? How far are the values from the actual data set? How far are the values from the mean, not actual data set? How far are the values from the mean? Okay. And each difference is emphasized by square. Okay. So, so, so that's why the each difference is squared and that becomes like emphasis to each delta so that if there are other more values, okay, then that would not have much. How should I explain that? If there are more summation of differences, it's just simple summation, the impact of other change. So how should I say? The more the difference, the more will be the square. Say 1 remains 1 while 2 becomes 4. Okay. So just to emphasize the difference, we put the variance, and just to emphasize the difference, we put the square, and that's one of the reasons. The other reason of squaring is so that if one delta is negative, other is positive, it should not cancel each other. Okay. All right. So what we see is that variance is a good thumb rule because if you can just always think about taking a photo or looking at the shadow or converting a 3D object into a shadow. So if you think about it, the direction from which you are taking a photo should be such that such that you cover the maximum amount of variance. Okay. else you would not get much information, right? And the direction which is having the least amount of variance, that means the direction can be happily ignored, right? The direction can be happily ignored. So if there is already kind of a 2D photo and you're taking the 2D photo from the side, the photo of that, let's say you're trying to take a picture of this monitor of somebody, and you are taking the picture from the side, as in from the side of the monitor. So you will only see a straight line and you will not get much information. Therefore, that direction can be completely ignored. The direction of least variance can be ignored. Okay, and the direction of high variance is what matters to us. So 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 the way we basically convert higher dimensions to lower dimensions is leaving out those dimensions where there is no variance, okay, completely, and and keeping the dimensions which have highest amount of variance. Now we select the axis that preserve the maximum amount of variance, okay, and this loses less information than projections, okay, sorry. um So what we do is we select the axis that preserves the maximum amount of variance, correct? And lose less information than other projections. Okay. So essentially we will lose less information. And in case we are leaving out the axis which has maximum amount of variance, that means we are going to lose a lot of information. Okay. So in this one, we discussed yesterday. So the answer was the C1 would be the direction. C1, the C1 will be the direction that will be C1 will be the dimension of the plane on which we can project the data, because C1, if you look at C1, the variance is really high. It starts from here, goes till here. The distance from the mean, if you assume the mean is here, if you are considering it like a, so if you look at this data from this plane and you're standing here to take the photo of this data, this is probably the mean, right? And the distance from the mean is varying too much in this direction, correct? But if you are standing, say this side, right, you will get this kind of photo, which is if the mean is here, the variance is low as compared to this, right? The mean is here, the distance from the mean is these values, while in this case, the distance is higher, right? And now, if you look at the third one, it's further low. The distance from the mean of various points is smaller, right? So, so the impact of distance, say here, right? 0 is our mean and minus 1.5. So if you see the variance in this case, it'll be 2.25 from this side, 2.25 from this side, and you add all these numbers, you'll get huge number. Well, in this case, if you think about this one, it will be zero point 0.5 is 0.25, close to say 0.75 and so on, and so on. So you'll notice that the variance in this case, if you compute the variance, you'll find that the variance in this case is the highest. So we will choose C1 as the first axis, okay, on which the data can be projected, okay, and the second direction could be orthogonal to C1. Okay, see, the second direction could be second plane on which data could be projected would be orthogonal to C1. Okay, I hope this diagram is very clear to everyone. Everybody's convinced about this answer. Okay. All right. Another way to say the axis that minimizes the mean square distances between the original dataset and its projection onto that axis. Okay. So another way to say the axis that minimizes the mean square distances. Okay. Okay. And another way to find the axis that minimizes the mean square distance between the original dataset and its projection onto that axis. Okay. Correct. Correct. So Noor's point is that when we think about axis, the only directions that come into our mind is x1 and x2. Okay. So yes. So we basically instead of just removing existing features or existing directions, right? Existing dimensions, right? What we are going to do is we are going to find the planes on which we could project the data, and we would be creating new axes. Okay, we would be creating new axes. For example, here we are creating new axis called C1 and C2 and C3. So there are many axes that we can create in order to maximize the variance on those axes. Okay. All right. A question is the axis determined on cosine similarity? No. The axis is determined based on again the variance. Okay. And okay. Now let me demonstrate this case. Sorry. All right. So here, this is what we've tried to plot. And okay. All right. So this is what we have tried to plot here. I think it would be good exercise to understand this code. Probably you can understand the code in your own time. And because when you are doing analysis, you might need to understand how to plot the data. Okay. All right. So you can take a look at the code and try to understand it. I think you can figure it out, most of it. All right. So basically, this is what we have tried to demonstrate in this. So we are trying to pick an axis which is having the maximum variance. All right. Now, so it's actually far more easier than it looks. Okay. So basically, we use an algorithm called PCA. Identify the axis. First of all, we find the axis that accounts for largest amount of variance in the training set. So whatever is your data, whether it's an image, whether it's any kind of data that you are specifically in case of supervised learning, or maybe unsupervised partially, you want to identify those axes that account for largest amount of variance. Okay, that becomes your first principal component. Then you pick the second axis which is orthogonal to the first one. Okay, that accounts for the second largest. And remember that this second axis, there could be many such axes which are orthogonal. Okay, but there would be only one which has the second highest variance. Okay, or you can say out of all the orthogonal axes, which are orthogonal as in kind of perpendicular, but when it comes to planes and more than 3 dimensions, we generally use the word orthogonal. Okay, all right. So it provides a second axis which is orthogonal to the first one that accounts for second largest. All right. Now, in the same way, we'll continue this till the end. Okay. The general thumb rule is if the if we are covering the total variance of 0.95, we should not go beyond searching for rest of the 0.05. Okay. So basically, the idea is we find the first axis which is having the max variance, and then we find the second axis which is orthogonal to the first one and orthogonal to the first one, but is having the maximum variance, and we continue this process. Okay, so the unit vector that defines the ith axis is called the ith principal component. Okay, so first principal component, say, is C1, second principal component is C2, third principal component is C3. C1 is orthogonal to C2 and C3. Okay, sorry. So C2 will be, I think, yeah. So C2 will be orthogonal to C1 and C3 will be orthogonal to both of these. Okay, C3 should be orthogonal to both C1 and C2, and that's how we define axes, correct? And why are we doing orthogonal? Anybody? Why are we doing orthogonal? Okay. Why are we looking for second axis that must be orthogonal to the first axis? Okay. Right. Right. So basically, when we are looking for orthogonal, meaning perpendicular, right? So the impact of one axis on another is zero. Okay, let me put it this way, that if you, let's say, if we have, okay, Okay, if we, let's say, have um, w- one axis this side and other axis this side, right? And if you project this, and these are orthogonal to each other, okay? So if you project this on this, what will be the result of projection? If you project 0, right? Yes. So um, basically the result of projection, result of because the impact of one axis on another axis is almost 0, right? When you is 0 when it comes to the orthogonal, right? Therefore, we had chosen the data, we had chosen the first axis such that there was max variance, and now we are choosing one direction, one second axis which is orthogonal to the first one, such that it has the maximum variance. Now this axis will not have any impact from the other axis, right? Because it's orthogonal to this one. So that's the sole idea about axes, dimensions. They all are perpendicular to each other. Okay, they all are perpendicular to each other, and so on, right? So there are many more physical connotation to this thought. Okay, so if you think of a feature set as somebody's love for music, that's one dimension, and somebody's love for, say, maths, right? So these are two features, right? Let's say we are listing down people, and first row is person one, second row is person two. In first column we put love for music, and second column we put love for maths, and so on. So we will have many such dimensions about a person, right? Now, if we have to understand people's behavior better, so we'll have to find an axis, because there will be many people who love music as well as who love maths. So there could be a relationship between music and maths. So they may not be completely orthogonal to each other. These two dimensions, music and maths, may not be orthogonal to each other. Therefore, we'll have to find a new dimension in case of people's behavior, which are orthogonal to each other, that people who have this feature don't have these features. Or this feature does not have an impact on the other side, right? So that's the idea about finding the orthogonal behavior, okay? Orthogonal planes. So that the, all right. So basically, the that's the main the main part about the principal component. So I can actually probably the example that I gave, I could probably um, draw it some of the time. Okay, so but I think you got the overall idea. All right. Now, finding principal components which are orthogonal and have the maximum variance. mm, Okay, so it has two parts to it. First one is finding the principal component. So we basically we basically do it using SVD technique. SVD is called okay, singular value decomposition. Okay, this is based on something called eigenvalue calculation. It divides the training set into the dot product of three matrices: U, sigma, and VT. While in this, the transpose V contains the principal components or unit vectors. All right. So basically, it will if we will basically use the SVD technique to find out V's, and then we will iterate over the V's and find out the principal we want to find out which principal components do we want to keep. The first one will have the um, highest first axis will have the highest variance, then second, then third, then fourth. So and so on. So we'll just pick some of these and ignore the the ones that are towards the last. Okay, so SVD can be implemented in Scikit-Learn using the code below. It's actually a standard linear algebra package. Okay, so okay. Okay, very good question, Abhinav. Question is, how many such accesses should we find? I mean, where to stop? Correct. So we will find these all accesses first, then we'll go from left to right, and we'll basically go till the point we have covered 0.95 of total variance. Okay, so that's the idea, and we'll sorry, as long as we are having we will basically ignore the accesses with lower variance. In simple words, we will ignore the accesses with lower variance. That's all. Okay. All right. So the meaning of U and sigma we can for now ignore. Okay. So it's basically the standard, the singular value decomposition, and we use that to find the V's out of it. All right. All right. Yeah. For now, we can ignore the U and sigma, and we can talk about this. Now, coming back to it, so the first thing is we must center our data. So this is how we are centering our data on this. Here we are doing it on 0th axis, but we can do this on all the axes. So our data here is centered. Now, next thing is, important thing is that we are using this linear algebra package, np.linalg.svd and xcentered. And this is going to give us the principal components in V. V will contain the principal components of this data. So let me just take a look at it. So this is where it is. So we are saying x equals x centered, and okay, and then we have, okay, yes, T for transpose matrix. Let me just show you what's inside X. So this is our X. It has 2 columns. Okay. And here, so what we have is X centered equals X minus X mean. So we are computing the distance. We basically making making it centered. Okay. And this one, this is where we're computing the U and S and V, out of which we're going to only stick with C1 and C2. So you can see that this is our one axis, this is our another axis. All right. Okay. So question is, how many components? We did not use US. We are only focusing on the V, which is what contains the principal vectors. For now, we will skip the definition of U and S. Okay. Now question is how many principal components are we printing in the above code? 2, correct? Also, let's just take a look at all values here. Okay, so we could say this is what V looks like. Oh, it has only 2 axes actually. Okay. And when we say V dot T, Okay, this is how it is. Okay, you can see the difference between V and V dot T. Oh, it's a, okay, so no matter how we do V or V dot T, it's going to be the same answer. All right, in this case. Okay, so all right. Now, well, so once we have found the principal components, now we need to do what we need to do is we need to project the original data set onto the principal component. And we have already seen in the linear algebra session that a vector V can be projected onto another vector U by doing a dot product, and projection of, say, V on U. This is V, and this is the shadow of V onto U. This is that shadow. This is called projection. Okay, this is called projection. So it's as if somebody has thrown light from this direction onto this vector, and this is the shadow that has been casted on you. So this line is called the projection. Okay, the length of it as well as the direction is same as u, while the length is computed by the way of u dot v and divide by this. So overall, the projection as well as the direction is computed using dot product and dividing by the length of the magnitude of u multiplying by u. Okay, so that's how it is. Projection of v on u is this. All right. So if you think about unit vector is when you multiply a vector with its magnitude. So when you divide this here and here, so all we need to do is we get the unit vector of u, do a dot product with v, and then and that the value that comes out will be a scalar value, and then we multiply that scalar value to u. Okay, as in to that unit vector. So basically that unit vector will give the direction, and this one will be the length of it. Okay, so that's how we're going to do that. The same thing can be applied on the planes. Here it's just two vectors, but the same thing, if these two would have been the big planes, then also if you want to count, if you want to if you want to find out the direction and the magnitude of the shadow of this plane onto this plane, the same mechanism will apply. All right. Now, the original training dataset X can be projected onto the first D principal components, WD. Okay. So similarly, the original dataset X can be projected onto the first D principal components. We are going to call the first D principal components as WD. Okay, and instead of doing individually, let's say we have a data set X and we are going to project on first axis, second axis, third axis. Instead of going to do that, we can do the entire thing in a single shot by doing a dot product, by kind of multiplying in this way. Okay, so all we're going to do is take the original data set, multiply it with the vector, multiply it with the matrix containing all your principal components. So first D components of the V, right, is what we are going to multiply. Okay, it is composed of first D components of the V obtained in the SVD. Now this will reduce the data set into this. Okay, this will be our resulting data set. So essentially all of the data set is being projected into new dimensions. So it's kind of reshaping the data such that we are we are looking at the data. We have the data in the directions. The data is being transformed such that such that the axes it has, the new axes it has, have the increase, if has the maximum variance, or you can say decreasing value of the variance. So this one has the highest variance, this one has slightly lower, and so on. Okay. So the PCA algorithm involves two steps. One is SVD, the single value decomposition, and the projection of training data set onto the orthogonal principal component. So two parts, SVD and projection. Okay. So either we could do using Scikit-Learn, we could do in parts, or we could use the PCA algorithm as such. So here are the two parts. The left one, the left one is the left one is in two steps. First, we centered our data, then we computed the SVD. Here we got V, and then after we got V, we picked up some axes, say two axes here, and then we did the dot product. So this is our new data, new projected data. Now, this same algorithm could be done in this way. Okay, so here we're just using an existing package called PCA. PCA has got, we're passing two components. So PCA, we are just telling that we want two components as a result, and we are saying PCA.fit transform X. So it is basically, in a single shot, it is doing both the things. Okay, it is doing both the things in a single shot. So we can use either of that. All right. If we need these vectors, we want to do other magic, like we want to iterate by ourselves, find out something else, then we may choose this technique. And if we are just looking for PCA, then we can simply use this. Okay, please remember that this SVD takes some amount of time. Okay, this SVD takes some amount of time, and while the dot product does not consume that much time. Okay, so let's take a look at it. This we have already done. Okay, this we have already discussed. Now, here we are picking two axes and then projecting the data. And if you want to just use it up front, we could use it in this way. All right. So it was pretty simple to just project the data into two axes. My question to all of you is, do you think there could be many other uses of PCA than only this? Can we use PCA to compress our data? Because essentially, okay, question from Abhinav is, why do we have to center the data for SVD? So the SVD algorithm wants us to center the data because otherwise it doesn't perform very well. Okay, and I would need to understand why it needs that to be done. Okay, all right. So that's the part. Okay, if somebody has a better answer for that, be good. Now, the other thing that is very important is something called explained variance ratio, right? So the PCA, while it's doing its job, it's also basically retaining the various variances, right? It's also retaining the variances. Yes. So Yeah, before the question, I was asking this, can PCA be used for other things, right? So since PCA retains only the valuable information, and we ignore the dimensions which are not relevant at all, right? Or we remove the dimensions which are not too much important because they have very few data. So can there be any other use? Can there be any other use other than reducing dimensions for machine learning? So all we are trying to do is we are trying to make our dimensions smaller so that our previous algorithms, whatever we were doing, they uh, it becomes easier to do those operations. Okay, so yes, thank you, Gopi. You can compress an image as well. So if we first of all, if let's say if we basically use PCA and translate existing data or existing image to new dimensions. So what ends up happening is though data is encoded in a new format, and also it'll be quite maybe in case of MNIST, the data is going to be around 20% in size. So you could achieve a decent amount of compression without losing much information using PCA, right? So image compression can be done using PCA. Okay, we're going to talk about it, Gopi. Okay, good. So here again, so to find out what are the various components variance, right? And I'm going to show you using the PCA.explain variance ratio. You can see that the first dimension, the first component was having 95% of variance, while this one is having this much. Okay, so so you can see that the ratio, the contribution to of the second axis is really low. Okay, and therefore, if had there been more axes below 0.95, below 0.05, we could actually ignore that. Okay, so how to select the number of principal components? A question from Abhinav. The principal components should explain 95% of the variance in the original data set. And okay, now if we are let's say reducing number of dimensions, right? We should look for principal components which can explain 95% of the variance in the original data set, right? And if we are our objective is visualization. If you want to visualize, we can at most keep 2 dimensions or 3 dimensions. So if our objective is for machine learning, then we should look for the dimensions that should cover that should explain 95% of the variance in the original data set. Okay, so calculating the variance explained in Scikit-Learn, so we can basically use the explained variance ratio, and we can use something called cumulative sum. Cumulative sum is nothing but we go from left to right, keep adding values, and that should tell us that at which point are we reaching the 9.95. Okay, so explained variance ratio is basically um, made up of many values, okay, from left to right, and these values all basically sum up to 1, all sum up to 1. Okay, and and all we need to do is go from left to right, find the point where we reach point 95%. Okay, and that's it. And how to do that? Basically, after doing the PCA, after doing PCA fit, we get this explained variance ratio. If this has like 20 dimensions or 20 principal components, then there'll be 20 values. So we go from left to right doing the cumulative sum. I think if I show you how does cumulative sum work, then you will get a better picture. So if I say 1, 2, 3, 4, 5, right? So it's basically summing up 1 plus 2, right? Then it became 3, then 3 plus 3 is 6, then 4, then 5, then and so on, right? So this is how it is happening. Okay, so this is cumulative sum. So cumulative sum is basically, it goes from left to right, summing up the value till that point of time. So after we have computed the cumulative sum, the next thing is find the argmax. Argmax is return the index at which we reach a particular value. Okay, so we could say, okay, so let's say this is our cumulative sum equals this. I'm just writing one example, and we're saying argmax, and we are saying cumulative sum greater than 5. Okay, so we want to find out the in this in array at what point we are going beyond. Okay, so cumulative sum. Okay, so at the index, at this index, okay, let me just print both the data sets. I'll give you a better picture. So here you can see that uh, 0, 1, 2, right? This is where it crossed the cumulative sum. So that's what is being done here. So here when we fit here this one, okay, and we compute I'll just print all of these values. That'll make more sense. Okay, so if we print say PCA dot explained ratio, okay, and here we are say printing the cumulative sum, okay, and then we are printing the resulting one. So these are the two values, right? And when we do this is what the explained variance ratio is, and when we say cumulative sum, so this is same value, and then this plus this is 1, right? So the moment right, the here we are saying that give me a value which is greater than cumulative sum. Give me the index at which the cumulative sum is going to be 0.95. So first we'll compare here. Yes, it reached. So it'll return 0, and D is going to be 0 plus 1, that is 1. Okay, so D is 1 more than the index. All right, is it clear to everybody? So what are we doing here? Okay, we're basically adding 1 at the end of it. All right, that's why the result is 1. All right, so this is how it looks like. So we are using two functions from NP, NumPy. One is cumulative sum and other is argument max. Okay, a question from Kamal is, can you explain how is the PCA, the explained variance ratio computed? Okay, so every component, C1, C2, C3, all of these components are having their variances, right? So it keeps all those variances, and then what it does is it sums up all the variances and computes the ratio, okay? Computes the ratio of the total variance. It's kind of standardized variances of various components. Okay, so the variance ratio is kind of standardized on the scale of 0 to 1. Okay, so sum up all the values. So there are going to be, let me show you here. So all it does is every component is having variance. right? C1 is having a variance, C2 is having, while computing these components, it did compute the variance, right? And at that point of time, at that point of time, when it computed the variance, it basically summed up all these variances and then divide every variance by the sum. Okay, so that becomes kind of this ratio between these. All right, great. So this is how we can compute we can find out the number of principal components, and this is how we can reduce the dimensions. Okay. Also, interesting part about Scikit-Learn is that they keep on updating the library. So the PCA algorithm itself has, if you pass n components as float, okay, and you pass the number of components as 0.95, instead of just instead of returning you the number of components, what it is going to do is it's going to return those many number of components for which the cumulative sum reaches 0.95. Okay, cumulative sum reaches 95. All right. Okay, so yes, the np.argmax cumulative sum is actually 0. Okay, I'm going to show you this. So yes, it's actually 0. Okay. Now, so all of these steps, whatever we did here after PCA, can be done without these two extra steps by just specifying the n components equals 0.95, right? So if you specify this value as float, it will act as if we are looking for a particular the variance ratio, the cumulative variance ratio. If we specify this as a number, then that means that we are looking for those many dimensions. Okay. All right. Now, one way is, okay, a question from Kamal is, when we just do PCA equals PCA and we do fit, yes, and then it calculates all of the components equal to the number of components in the number of dimensions in the beginning. Yes, that means equal to the actual features in the data. It just orders them such that on the leftmost has the maximum variance. The second one has the second highest, and so on. Okay, that's how it arranges them. It basically creates, or it might keep the existing dimensions based on the maximum variance. Okay, so yes. So all it does is compute the SVD, then gives you those many records. Okay, because we need to transform the data set as well, right? So we need to do the dot product. So it does the dot product. PCA does the dot product. So it does both the things, doing the SVD and projecting the actual data, both the things it does. Now, okay, the another option other than just doing the computing, you're just trying to do the um, keep only 95% of the variance, cumulative variance. The other way could be that we draw a chart or draw a graph between the number of dimensions and explained variance. Okay, so on one axis we have number of dimensions and the explained variance. Okay, so we'll keep on increasing the basically we keep on uh, increasing the dimensions, and we keep on seeing how much we have the explained variance. Okay, so so after a point it will be like, so after a point of time this will become stagnant. Okay, it'll start growing, it will basically kind of become static. It's like an elbow. In the initial dimensions, the 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 graph grows really fast, and afterwards it kind of becomes stagnated. Okay, so 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 you would like to maybe pick the value somewhere here or here. Okay, so once you draw the graph, you will have the clear picture. Okay, so we can actually draw the graph really easily. Okay, okay, let me just see. Is it in the second one? Okay, no worries. So I think we'll just skip this. Okay, okay. So I'm just trying to figure out which one should I use, this one or this one. Okay, all right. So okay. I think the copy one is updated. I'll fix it after the session. Okay. All right. Yeah. So I think there's no graph for this one. Okay. So we will basically fix it later. Now, the idea is very simple, that basically you keep on increasing the dimensions, and you plot the graph. Okay. You compute the dimensions. Okay, it actually can be done simply by just plotting the cumulative one. Okay, it can be done simply by plotting the cumulative, the one that is having the cumulative one, but we don't have actually the data to do this. Maybe in case of MNIST we'll have many dimensions, so we will be able to do. Okay, so one way is to use the way we have just done, the 0.95 kind of 95% kind of variance. Or in case you don't want to lose information at all, maybe you may want to go for like 98% of the variance. Okay, and okay, so let's say you just are okay with only losing 0.02% of the total information, then you can just go for 98%, and instead of 95%. Now, going ahead, so the another aspect of dimensionality reduction is the compression of data, right? The question that I asked. So a number of times we want to reduce the size of our data, not only as part of machine learning, but also as part of the other other exercises, right? As part of the other works. So we could use the PCA there also. Okay, so that, let's say you have certain kind of data which is not image or audio is not anything, but you want to compress this data. And remember that most of the data could be compressed because as we talked earlier, that data naturally in naturally data, if we have it, if it has too many dimensions or too many columns, naturally it is going to be sparse. And when data is sparse, you can always bring it down to lower dimensions. Okay, so if you want to compress the data, you may use the PCA as well. Okay, so the training set takes up much less space when you compress it. For example, if we apply PCA to MNIST, basically the original image was 28 pixel by 28 pixel, and it basically each image was taking 784 pixels, and it has 784 dimensions. If our objective is to analyze these images only, then maybe we can figure out which of the dimensions are useless in these images and ignore those dimensions, and thus we will be able to compress our images. Let me demonstrate. So, so here, after applying PCA to MNIST, the number of dimensions will reduce to 154 from 784 features. Okay, and these 154 features would be keeping around 95% of the variance. Okay, we'll be just losing on 5% of the variance of the data. Hence, the training set is 20. This will basically bring down the training set to 20% of the original size. Okay, let me show you this. Okay, let me show you this. Right now, here we go. So this is the actual MNIST, the X train here. Yeah. So here we go. Now here we are basically doing the standard that train test split. Okay. We want to. Okay. Now we imported the packages. Then we are loading the data. Then we are picking the data and the target. Then we are splitting it into train and test. And here X is X train. Now we are using PCA. We're using PCA, and we could actually do n components equals 0.95, and we'll get the same result, right? So if you do that, the number of the dimensions it has picked is this. Okay, let me import. Let me run everything above. Run all above. Okay, so we get how many? How many? 154. The same thing could be done using, say, here instead of these 3 steps, could be done in two steps. Okay, so here we get the number of components that would be required for 95% of the 95% of the variance. Now let's take a look. Now let's say let's say we want to, this is the reduced data set. Okay, after these steps, this is the reduced data set. Okay, so this is the reduced data set, and these are the components that have been used. So both are exactly same. Now, and the variance ratio is this much. Okay, you can see that. Okay, what we have done is we have just computed the sum of all the remaining principal components, so we can just take a look at. So these are 154 values, and these are 154 values, and the sum of which is 0.95. Okay, All right. A question from Vinta is y plus 1 because the argmax gives us the index and the index starts from 0. Therefore, we are adding 1 to mark that these are 154 dimensions, right? If we had like it has returned 0, 1, 2, then we will say the last value plus 1, right? To get the total counts. All right. Yes. So what we did was we changed our image to to something else. This image is something else. Okay, because they are different dimensions completely. Okay, so if you try to plot it, it wouldn't make much sense. Now, after this image is changed to another dimensions, we could retransform it by doing the inverse transformation. Okay, so we after we have reduced our image to something, we could do the inverse transformation using the same PCA algorithm. So this was the original image. This was the original image, and this is after reducing it to 154 dimensions. Now after we have removed the remaining dimensions, we are converting it back to the original using inverse transformation. So this is the original image. Okay, I'm sorry, we are converting it into the image because this is not an image. This is something else because we have projected data on different dimensions altogether. So if we try to plot this, it wouldn't make sense. So we are changing back this to the original one without the remaining dimensions. We are just keeping these many columns. And when we do inverse transformation, then we get this recovered image. And let's see how it looks like after plotting. Okay, let me just start from above. Okay, let it finish. So you can see here that it has basically, this is the recovered image and this is the original image. So you can see that there is slight amount of data loss. Okay, slight amount of data loss. Can you notice the difference? So this one has become little low. And do you see any differences between left and right? Just that the right one is little more darker and left one is the white one. Okay, a question from Noor is it not 784 pixel again? It is going to be 784 pixel, just that those dimensions, some of the values on those dimensions have been removed. Okay, so 6 on row 4. Okay, is there a difference? All right, so it has removed the, yeah, there have been only minor losses. Okay, only minor losses, right? So, right, there has been only minor losses. Okay, so here we are plotting the x MNIST and we are plotting x MNIST recovered. So we are not changing the size or we are not changing anything. Okay, we are just okay, we're just printing original here and recovered here, and we are just subplot and subplot. We're just giving that name. Okay. So what you see is here, right? Okay, so basically the image is kind of darkened. The white background is gone because remember what happened was um, we found that the white space around the values were useless, correct? So what it did was it removed all of those values as one because white means one, correct? And the 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 black means 0, right? So what it did was it basically deleted all the white space around the values, and that's why when we are reprojecting it, it is darker. Okay. Okay. So so the gray background is the result of that removal. Remember, if we look at that here, so all the values, all the pixels which are around here, they're all lost. This information is lost. This information contained only white background. So this information is lost, and that's why it has become the backgrounds have become dark. Okay. A question from Kamal. Different images after PCA can have different number of dimensions. Like in this case, it was 154. It could have been even lower. Right, right. So basically, on an average, for all of the images, it found that the the so basically when we removed the dimensions or we computed the principal component, it was happening for all images together. A question from notes. So I thought if we remove dimension, it will fit to lesser number of pixels. Okay, so yes, basically that's the interesting part about dimensions, that the way we look at dimensions, we look always in X and Y kind of dimension. But for PCA, every pixel was a dimension. Okay, every pixel was a dimension, and when it computed its own kind of images in its own kind of dimensions, those dimensions do not make any sense to us. Those 154 dimension it computed, they do not make any sense to us because they do not have any physical connotation. Okay. All right, a question from Node, but it replaces white with the gray, still storing information in extra pixels. Yes. So it did not completely delete all pixels there. Okay. But it kept some amount of tiny bit of information. When we did the inverse transformation, it got imposed with the black color. Okay. So the value around these is lost, that information, because that's not really required to present these images. Okay. All right. So question from Gopi is there are still 784 pixels except in the lower dimensional space. Yeah. So when we did the inverse transformation, we basically projected back those how many dimensions? Well, 154 dimensions. 154 dimensions we projected back on 784 dimensions. Now, when we did the projection, it did the extrapolation. Okay, it did the extrapolation, and that's why the black color got projected on the white background. I mean, that's how you can think of. Okay, that's why it is a gray. Okay. Question from Vinta is, however, the original one are more sharp. Correct. Are original one more sharp, or is it just that us? Or maybe they are looking sharp because there is no white color. There is white color around them. 5% sharper. Okay. Okay. So I think that'll be really difficult. So what you see here is just because it has to project back and that's why those extra white spaces came. But from the data perspective, the data is kind of really good, and we can test out our assumption by feeding this data to the MNIST that the classifier that we built in the first session, and observe, is it giving us great results? Okay, is it giving us great results? A question from Noor: is there a way to compare the original and the recovered data? So this is basically a way of comparing, and sometimes it is not possible to compare. We'll talk about that part also. Okay, Gopi is saying that it looks sharper to me. It is image compression. Think about high resolution image being more sharp than low resolution image. Right, right. So, but we could try comparing by substituting the gray color with white and then see how it looks. Okay. Now, question from Kamal. Okay. Question from, can different images when compressed have different sizes? Maybe few could have no impact on compression. Maybe, yeah. So question is, can different images when compressed have different sizes? Yes. Right, right. So what has happened is, it basically, when it was looking at the data, it was looking at the pixels, right? And it looked at these pixels with from all possible dimensions possible, right? And computed the variance. So when it basically, the image that is outlier, okay, might have little bit of smudging around, right? So you can see that this one looks less sharper, better sharper. This one looks rough. Okay, so good. So there could be many scenarios. Okay, so can different images when compressed have different sizes? They could have different sizes, yes. Maybe few could have no impact on compression. Mm-hmm, mm-hmm. Maybe, but the chances are very low because variance is being computed on all of the images, right? And in variance, when we compute variance, each individual deviation has has a higher impact. Okay, so the one that is an outlier image will have a higher impact and will be counted. Okay. A question from Noor is, I think we need to pass both the image to the same algorithm and compare the outcome. Correct. Okay. Both images as in? Question from Mintao is that why is gray background come to the recovered one, right? So remember that when we did analysis, we found that the pixels around, okay, let me just show you. When we were discussing about the pixels, right? And even in the decision tree, we found that these pixels had no impact at all, right? So these pixels have been kind of ignored. All the pixels around here, they have been ignored. Okay, that means those are the dimensions that have been deleted, right? And when you and What does it mean? Here, when we say dimensions value is 0, that means the value has become black, correct? So since we deleted the pixels and we are those all values have become 0, and when we have reprojected it, so some of the whiteness from here and there has been projected there. That's why it has become a bit of gray. Okay, so that's how you can visualize. Okay, so basically the white background has been deleted as part of the principal component m- analysis. We just wanted to keep few dimensions, and the ones that were removed were mostly the ones that were around it. So you can see that here so let's say take a look at say this point, right? This point is black, correct? So should it have an impact on our values? Okay, so like this pixel, these particular pixels, okay, maybe this side of the pixels. So it's actually difficult to visualize it that way. So pixels around your core one would have impact. Okay, the one, say the 4 one, right? It's going beyond this point. It's longer. So those pixels are less important and therefore have been removed. So you see this length is shorter and so on. So basically, it's important to understand that what pixels have been deleted. Okay, pixels have been deleted which are as per this diagram. Okay, all right. Okay, let's move on. Yes, I'm sorry to use the word deleted. It's basically when I say pixel deleted, it actually means the pixels value have been reduced to 0, which means black. Okay, so all right. So this is basically after recovery. This is the data that is there before inverse. That is the one that is compressed and so on. All right, so let's move on. I think that's good enough analysis. Okay, all right. A question from Kamal is, as in to achieve 95% of the coverage, it had to consider the number of features is 154. Correct. Okay, good, good. All right. So what we learned today is the how do we reduce the dimensions by projections. Now moving on. Okay, so we also talked about decompression. We can see that. Okay. So this is called reconstruction error. Okay. Some of the while some of the dimensions were removed, some of the information was lost. Okay. This is called reconstruction error. Okay. Now the problem with PCA, we also call it batch PCA. It requires the entire training dataset in the memory to run SVD. So since it's a matrix calculation, matrix multiplication, and things like that, the entire data needs to be loaded into the memory. Okay, that is one drawback of PCA. This is where incremental PCA comes into play. So what Incremental Pca does is it splits data into mini batches and feeds one mini batch at a time to IPCA algorithm. And it's useful when you have large data sets. Okay, when you have large data set, then it's quite useful, and it can be useful in the cases where you want to do the online learning. Okay, so you can basically use the Scikit-Learn's incremental PCA class using partial fit function instead of fit. Okay, instead of fit and fit transform, you can use partial fit. Okay, so this is how you could do. So this is how you could take a look. So what we are doing here is, first of all, we are importing the incremental PCA. Then we're creating batches. We are also we are explicitly saying here number of component is this much, but we could say 0.95 as well. And here we are basically going from, okay, so we are splitting this data into 100 batches using a split and then doing the partial fit. All right. And once we have done the partial fit, we have trained our algorithm, and then we can do the transform. So this would give us the results. Okay, we are printing a dot here. That's why it looks like animation. Okay, so it has finished the work. All right. So you can use the incremental PCA in case your data is really huge and you are not able to load it into the memory. In those cases, you could use the incremental PCA. Okay, now, all right, so we can take a break here and then we'll come back. Okay, so let's take a break for 10 minutes. All right, so yes, I'm back. Should we start? Okay, so a bit of more theory. So using other than SVD, there is something called kernel Pca. It basically has some similar to the SVM kernel trick. It's also that same thing is applied here. So kernel trick can be applied to PCA. It makes nonlinear projections possible for dimensionality reduction. And this is called KPCA or kernel PCA. The important point to note about kernel PCA is it is good at preserving clusters. It is useful when unrolling dataset that lies close to a twisted manifold, right? So kernel PCA is again a mathematical trick which can be applied to PCA to make it possible to do nonlinear projections possible. Okay, so there are many. So there are many kernel PCAs there. Some of them are linear, RBF, and sigmoid. Okay, so this is called the linear PCA, linear kernel. This is RBF, and this is sigmoid. Okay, we'll talk about this again. And right, so let me go down here. Okay. Um, I think I did not show you how does I did not show you how does the incremental PCA work. Incremental PCA is essentially for the doing it partially. Now there was one more interesting point that we left, probably it wasn't there in the presentation, that when the data is not fitting in the memory, you could create something called ME map. Okay, you could create something called MEM map. What does it do? It basically creates the data in the disk and loads only the partial data when required. Okay, this is a very, very important utility provided by NumPy. So if you have, let's say, a huge data, say uh, let's say this data is in this file, and we would like to load it whenever it's needed instead of loading entire thing in the memory, we could create a memory map, and then we can map the MNIST here. Okay, so afterwards we can use that. Okay, so basically the idea behind memory map is that we only load the data that's required, and whenever we need more data, it can automatically load it from the disk when it's needed. So here, in case of incremental PCA, we could also create a memory map, right, from the file. Instead of loading the entire data, we just keep the kind of a handle to the file, and then we call create incremental PCA there, and then fit it on XMM. So whenever required for this, whenever it needs to load data, it'll read from the disk instead of reading from the memory. Okay, so it's kind of paging or buffer, you can think of it, that some of the data is in the memory while the rest of it is in the disk. Okay, and we could use this in case our data is something that is not fitting in the memory. All right. Okay. All right. This is the one I'm talking about that I kind of skipped in the presentation. All right. So basically, what we just learned is that we could use memory map, experiment with the memory map, and you could actually use the memory map in the other algorithms as well. Specifically, if your algorithm loads data in batches, okay, and then it can utilize the memory map. Okay, if it requires only part of the data at one point of time, then memory maps are pretty useful. Okay. Okay, a question from Minta is how many important parameters are there in the PCA? So one is the components that we are using. So it'll basically the components that are useful to us. I'll just do that here. So, okay, so these are the various components, right? And the other parameters that are useful is explained variance ratio. That's more important to us. Okay. And what else do we have here? Okay, number of components is another, and number of samples seen. and singular values also if needed, but that's not much required, okay, for at this point of time. So you can take a look at it. So mostly we'll be using explained variance ratio and the number of components as well as components. Those three are more important than the other ones for us at this point. Okay, now, so this is what we did, and this memory map would make sense with incremental PCA because it is going to load only partial data. It is not going to load the entire data. Okay, a question from Binta is, where can I check these parameters? Just search for incremental PCA or PCA normally. You will get the you will get the manual. Where is the documentation? Okay, so this is the documentation where you could take a look at the number of components and copy the batch and so on. Okay. Good. Next is actually the Scikit-Learn has got probably the best documentation available for the components, and that's why it's generally preferred choice of any machine learning data scientist. Okay, so all right. A question from Gopi is memory map similar to the setting low memory to true in pandas data frame? Oh, that I don't know. Actually, I have not used that low memory tag with pandas. Okay, so could be similar. Now, the second thing we talked about is the randomized PCA. So randomized PCA is a stochastic algorithm, okay, to approximate first D principal components. It's actually faster. It's dramatically faster if your total number of dimensions are really huge. Okay, so what it does is it basically, instead of iterating over all, it randomly picks the components. It picks the components randomly, and that decreases the total size. Okay, so we are not going to go into the details, but in case your dimensions are really huge, you can use the stochastic way. Instead of iterating over all the dimensions, it will quickly try to figure out some D dimensions. Okay, so it does that. So here we say ran SVD solver is randomized. Okay, so if we say SVD solver randomized, then it will try to basically do stochastic, or will try only few options instead of all. All right. Now, here is that we are trying to show you the difference in time between. Okay. Okay. So again, doing the PCA takes a lot of time, and if total number of dimensions are really huge, it'll take a huge time. And in those cases, as you can see, this is the time that it takes for PCA for the work. And this is if there are n dimensions, then it becomes m into n square plus on cube, right? But if it does it on D principal components, it will basically is going to be, if D is lesser than N, this time dramatically get reduced. Okay, that's what is the randomized PCA. Okay, so it is trying to show you the time taken in order to do the computation. So the normal PCA is taking 1.6 seconds. Okay. And this way you can actually measure the time using you basically starting the time and so on. Okay. Incremental PCA is taking 14 seconds. Okay. And okay. Okay. So which one is the last? So regular, incremental, and randomized. Okay. So as you see that as the number of components start increasing, the the randomized PCA is taking less time. Okay, is taking less time. Although there's not much difference, though incremental PCA is taking more time. Why? Because it's reading from the disk the data every time when as soon as it finishes the first batch. Okay, that's why. Okay, that's why it's taking more time. All right. So you can see that there is a bit of difference between the PCA in the PCA here. Okay, you can see it's a little faster, while in case of 10 components, it's actually slower, the randomized PCA. Okay. All right. So that's pretty much. Okay. So when the n keeps on growing, the if you keep the d smaller, then it becomes a little faster. Okay, number of components. Okay. All right. Now that was it. Okay. So here the time difference is not much visible between randomized and normal one. Okay. Otherwise it generally is faster. Okay. Next is okay. So we started talking about kernel PCA. So kernel PCA is basically a mathematical techniques which makes it possible to do non-linear kind of principal component analysis. This is good specifically when the projections that we are trying to do is non-linear. Right now, so far in case of PCA, we were basically projecting on linear, as in even though there were n dimensions in each plane on which we were projecting our data, in this case of kernel PCA, the projections are non-linear. There are three kinds of kernels. One is linear, other is RBF, third is sigmoid. We'll get into this. So basically, the way we use a kernel PCA is using the class called kernel PCA and providing the kernel equals RBF or sigmoid or say linear. Okay, so either of them is what we use. Okay, so all right. So this is what we are trying to do. What we're trying to do here is first we are importing kernel PCA, then we are making a Swiss roll, then that's the data set that we are generating. Okay, and all right. So then we have a, okay. So looks like gopis are, hungry or something. So we have, yeah. So this is linear PCA, and yeah. So kernel PCA is basically a variation of PCA, just like in the SVM we talked about a mathematical technique, but we did not go into exact maths. What goes in the kernel SVM? Okay. So here, similarly, the PCA is there's a kernel trick to PCA, which makes it possible to do non-linear projections. Okay, so here we are creating three kernels. One is linear, other is RBF. These are three kernel PCAs, and basically these are nothing but algorithms that use a specific mathematical technique in order to project the data which may be non-linear. Okay, and right, there are some hyperparameters that, okay, here there's some hyperparameters and so on. Okay, so all right, now, so we have created these three algorithms. Now what we are doing is we are calling, where are we calling these functions? Right. So we are first of all labeling it, then okay, here. Okay. Oh, okay. So basically this is where till the for loop is from here till here. We are saying for subplot PCA title in this, right? I can actually make it separate. That will be better. Okay. Okay. This is easier to understand. Okay. So we are saying for each of the subplot and then the algorithm, then the title in the kernels. Okay. We're iterating over this, and we are saying that we are trying to basically reduce the dimensions, and then are we okay, this is the reduced one. All right, okay, and then we are plotting it. Oh, it's going to take a lot of time. No. Okay. So basically, while we are doing the PCA, while we are reducing the dimensions, we could use the various kernel PCAs with different kernels, and we could reduce the dimensions gracefully using the PCA. So you can see that here, even though it has reduced the dimensions, the data is actually kept intact. You can see it has taken the instead of destroying the data, it has kept it from this direction. Similarly, this is some RBF kernel which it has created this data set in this way. So here sigmoid is again has done this kind of segregation. All right, now if we had to do machine learning on this kind of data, it would be very much possible. Okay, because there is a way to draw a plane in this. All right, so okay, All right. Now, this is what we are trying to achieve. Okay. So it says that the kernel that suits it best is RBF kernel. Okay. So we have created these. So here we are using the grid search, and okay, I'm just putting these comments here. Okay, so here we are basically creating a pipeline of logistic regression and kernel PCA, and we are putting the various parameter grid here. We are saying that these are the various gamma functions, these are the various kernels, and then we are using grid CV and observing grid search basically does the grid search as well as the what do you call this, the cross validation. Okay, so here what it is doing is it's evaluating, it's checking whether kernel VCA is better or logistic. If the RBF or sigmoid, which one is better? So after the grid search, the one that we discussed in the first session, we observe that the RBF kernel is the best, and this is the gamma value. Okay, so that's a one way of deciding upon which kernel to use. Again, the grid search remains there as such. So grid search is still quite useful way of deciding on which algorithm to use, even though we have studied many algorithms. Okay, now, right? So selecting the hyperparameter, kernel PCA is unsupervised learning algorithm. So there is no obvious performance measure to help selecting the best kernel and hyperparameter. But since this is kernel PCA is used generally in conjunction with our, see if you look at the dimensionality reduction, it is a unsupervised learning kind of algorithm, right? Because you just give it data, it will reduce the dimensions. Okay. It just so happens that we are using kernel PCA in the case PCA or kernel PCA in the case of machine learning. So the way we do in case of our machine learning algorithms, what we do is we generally use the grid search in order to find the so we generally use the grid search using the in order to find which algorithm and which kernel works best. Okay, in conjunction with our normal classification or in normal regression models. Okay, a question from Abhinav, but in above diagram, our RBF was not keeping the actual shape. I think there was a lot of loss in RBF kernel. No, actually there was not loss. It was just there was no loss. It was just it is projecting the data onto some nonlinear projection. That's why the shape is coming out to be really, really strange. Okay. Okay. So that's why the shape is coming out to be really strange. Okay. And now reconstructing a kernel PCA is generally hard. The way in case so okay, let me right. So generally what we do is the way we did in case of image, right? MNIST data, what we did was we transformed the data and then we did the inverse transformation, and then we could compare various pixels and look at how much loss did we make, right? That is one way to measure how good the algorithm that we are using is. Okay, so but in case of kernel PCA, it becomes a little harder to do that. So let's say this is our original space, and after kernel PCA, this is what we get. Okay, it's there is a different kind of space you say projections that it has done, and it has found that this is one of the good way of projecting it. Now, here, the after doing the kernel PCA, this is the result that we get. And from this, if we try to reconstruct a pre-image and then compute the error, it's going to be hard. Okay, so there are two steps involved in reconstruction. Okay, one is mapping the higher infinite dimension, mapping to a higher infinite dimension feature space, and then projecting the transformed training dataset into a 2D using linear PCA. Okay, then the inverse of the linear PCA step would lie in the feature space, not in the original. Okay, so since it is infinite dimensional, we cannot compute the reconstruction point, therefore cannot compute the reconstruction error. Okay, so this, let me just go back here. All right, so one way was using the grid search. One way was using the grid search to find the best kernel. And in the grid search, one of the things that we could do is we could minimize the reconstruction loss. In case of kernel PCA, the computation of reconstruction loss is really difficult, because let's say this was our original space, right? This was our original space, and after applying the kernel PCA, this is what we get, the feature space. Now, this one that we got after the kernel PCA, we cannot have, even if we do the reconstruction, we are going to get really different image. We're going to get really different image. That's the strange thing about kernel. So after reconstruction, we get this kind of image, right? So there is no one-on-one mapping between these. We can't compare this with this. Okay, we can't compare this with this, and therefore the reconstruction is really difficult. Okay, the reconstruction is real. Let's say if you want to compare this point with something, then how would we compare? So even though we did the reconstruction, because of reduced dimensions, the shape has completely changed, and therefore therefore it's not possible to really compare this versus this. Okay, all right. And so what we do is we basically create something called pre-image. We create something called pre-image, and pre-image is basically created by applying the same dimensions to the original image, and then compare this with this. Okay, so let me see if I understood correctly. All right, so for reconstruction, we instead use something called a pre-image. So by finding a point in the original space that will map close to the reconstruction point, okay, we can find the square the distance with the original space, and then select the kernel and hyperparameters that minimize the reconstruction pre-image error. Okay, so all we do is, okay, first of all, let's say there was an original space, right? And then we applied kernel PCA. We got a different image completely. And then we tried to do reconstruction. When we did a reconstruction, the outcome that we got was completely different. We can't, there is no point like X here, which has a corresponding value in case of the in case of the original image. So no, actually I'm about this thing. Yeah. So we took yeah. So this is what we are doing. We are applying kernel PCA, and this is the reconstructed image. And so all we do is basically make sure is that we find a point on the original space that would map close to the reconstructed point. Okay, and The core idea behind what I understand is that we create a pre-image from the original space and then we compare the two. All right. So this is a bit unclear. So we'll see if we could do a hands-on and make it more clear. All right. So this is clear. Okay. Right. So correct. It is so distorted that it is difficult to reconstruct. And even if we reconstruct it, it doesn't make much sense. Therefore, we create something called pre-image and compare it with the pre-image. Okay, so that's the core idea. So let's take a look at it. So say we are applying a kernel PCA with RBF and this gamma value as we figured out in the previous steps. Then we do the fit and transform. So this one will do the reconstruction as well after, okay. And so after here we say, this is our reduced image, right? This is our reduced image after doing fit transform, okay. And then we do the inverse transformation from the X reduced. This is the one which has reduced dimensions, and this is the one that is reconstructed, okay. And what it is suggesting is that all we do is we compute the mean squared error. Okay. And using our grid search or using our other techniques, what we could do is we could iterate over various parameters. Okay. And we could iterate over various parameters and tend to decrease this squared error. Okay. We could iterate over various parameters and tend to decrease this mean squared error. All right. So there is a concept called pre-image in case of kernel PCA, which is what we use, what we use to compare with our reduced with the pre-image. Okay. So I hope you got the picture. This is actually you looking at the diagram is a little more confusing. This is better. Okay. So we compare instead of reconstructing, we basically compare the original, right? Here we compare the original with the pre-image. Okay, that's what we do, the mean squared error. All right, that's pretty much. Okay, so we just keep in mind that if we are using kernel PCA and we want to further optimize, what we can do is we can use in the first shot we could use a grid search to select the best algorithm with best parameters. Okay, and then in the second shot, what we could do is we could basically further fine tune the various parameters, or even we could do the grid search by by keeping the mean squared error as our criteria. All right, that's what is this. So yeah. Now the second part of the dimensionality reduction is locally linear embedding. Okay, so we talked about so far is the projection technique in which there was PCA. We talked about kernel PCA. The linear PCA is good in many cases, but when the data is non-linear, then we can't use the normal PCA. We will have to use kernel PCA, and basically there's no better tool than using the grid search. Now the other kind of uh, problems occur in kernel PCA is when you have the manifold learning, meaning when we have the Swiss roll kind of data. Okay, then though kernel PCA was able to solve it to some extent, but it's sometimes it becomes little difficult even with the kernel PCA. So that's the time when we use the manifold learning technique, and one of the techniques is LLE. Okay, so it's basically, again, it's a non-linear dimensionality reduction technique. The manifold techniques that does not rely on projections. It basically works by kind of unfolding data, keeping the neighbors of every data points intact. Okay, so it works by measuring. So what is it that we're trying to do? We are trying to reduce the dimensions of the data which is in the shape of the Swiss roll, right? So, and I think by the end of it, you will start hating the Swiss roll. And okay, so it works by measuring how each training instance linearly relates to its closest neighbors. Okay, then it looks for low dimensional representation where these local relationships are best preserved. Okay, and and so it is good at unrolling twisted manifolds. So we'll use twisted manifolds instead of saying the name which makes you more hungry. So it is good for unrolling twisted manifolds, and especially when there is a lot of not much noise. Okay, so all it does is it basically you will the way algorithm works is on a manifold, if we have the data points and we basically compute who are the neighbors, okay, who are the neighbors, and then once those relationships are computed, then we can look for low dimensional representation where these local relationships are best preserved, right? So when we unfold a paper, what happens is the paper remains intact, correct? We don't tear the paper. We don't tear the paper. What does it mean, tearing the paper? The nearby uh, nearby mm, what do you say, grains of the paper are intact. They're maintaining their relationship, right? When we are unfolding a paper, we are not tearing it. Okay, we're just changing the dimension. In the similar way, what it does is the LLE, what it does is it kinds of finds out who is everybody's neighbors, okay, and then hold each other's hands. That's the kind of thing it keeps in mind. So basically, it prepares something called weights in which it maintains who are the neighbors, and then what it does is it starts to looking for the dimensions in if it can be moved while the local relationships are best preserved. Okay, so that's the core idea about this. So let's just make the this is how it has unrolled it. Okay, this is how it has unrolled it. So we have created the data set. We have created the data set, and then we're calling the local linear embedding. So we are specifying how many neighbors we want to create, and then number of components. These are the hyperparameters. And then we are doing the transform, and then we are showing it. So you can see that it has unrolled the data set. It has unrolled the data set. Now we can apply our usual techniques. Okay, now we can apply our usual techniques. Okay, so in simple words, what we are trying to do here is we are first of all going over the data set, finding who are the nearby. How do you find the nearby data points? By computing the distance between the data sets. And so essentially, we end up iterating the entire data for every data point, finding the distance between each of them, and then keeping in mind that who are the top closest neighbors to each of the data point. And then we start to change the dimensions such that those relationships which we prepared earlier are maintained. Okay, all right. So here the manifold twisted data set has been completely unrolled. distances between the instances are locally preserved. So these two data points which were there on the roll, they are exactly in the same way. Okay. And it's not preserved on a large scale. Okay. While the leftmost part is squeezed and the rightmost part is stretched. Okay. And so on. All right. So this is what this is closest to what we wanted actually. Okay. So the way it works is for each training set, the algorithm identifies k closest neighbors. It reconstructs the instances as a linear function of their closest neighbors. More specifically, it finds the weight W vector such that distance between the closest neighbors and the instance is as small as possible. Okay, so let me just walk you through this. So here what we are saying is that find those W's for which find those W's, sorry, we are trying to find XJs, right? Okay, okay. Yeah, find those weights as in establish the relationship, right? These weights is what matters. So what we are saying is for each I, where I goes from 1 to m, for, hold on to each element, then find the distance of this element from every element in the whole data set. In the whole data set, multiply it with W and put, okay. So what is it that we are trying to do is we are expressing, we are finding this X versus this, okay. So all we are trying to do is find those W's for which the distance between X and Xj, all of other Ks, actually this one is supposed to be I from K, okay, and find the distance and find those weights. So for each training instance, the algorithm identifies the closest neighbors, K closest neighbors, okay, and then once it has identified the K closest neighbor, it reconstructs the instances as a linear function of these closest neighbors. More specifically, it finds the weight W vector such that the distance between closest neighbors and the instance is as small as possible. Okay, so okay, so basically it is measuring that distance, right? Finding that distance which is closest to these instances which are nearby, and then is maintaining that computing and calculating the distance in the neighbors. So first of all, before this process starts, it finds the k closest neighbors for every element. So out of those k closest neighbors, then he finds the distance between those k closest neighbors. Okay, it basically finds those weights which are minimizing the distance. Okay, or you can say that it is expressing xj in terms of xi by the way of w. Okay, so now once we have done that, there could be multiple ways of doing this. Okay, now once that is done, we map the training instances into d-dimensional space while preserving the local relationship as much as possible. So we basically keeping the same weight calculated in the previous step. The new instance should have minimum distance. So this time we're keeping the w as computed above. We are computing the w, keeping the w as above. We are changing xi to z, xi j to z, so that this w is retained, and this distance is minimum. Okay, so it's like first of all, me and you on this class, right? We are sitting in a class, right? And we have found the distances which are, we have found these w's which express the best you as me. Okay, that means this is the distance, or this is the way of measuring the distance. There could be multiple ways of measuring the distance, right? Here, the way it's measuring is how we can express any other point in terms of me, and that is W. So it's basically trying to minimize this distance between the other data point and me, and by computing the W. So you can always think of this W as how much far away are we from each other in this class. Okay, now we start changing our positions. We start changing our positions such that the distance remains same, and still we are closest. Okay, this W remains same, and this is what we are minimizing. So we'll start xi to z, as in we'll start changing all the values, all the uh, data points, such that this distance is minimum. Okay, so this is what the LLE does. So first, there are three steps involved. First is finding k neighbors, finding only the neighbors. Second is finding the weights, meaning computing those weights with which we can express all the neighbors in terms of that data point, and then constructing a low dimensional representation. Okay, that is again a complex optimization, because we have to iterate for each data point again. That means m square into d. D is number of dimensions in the final one. And then we have the weight optimizations. So we have this one is again a complex one. So for each element, we are going to iterate over k and so on. So it's m into n is total number of dimensions, m is total number of instances, k is the nearest neighbors. So first of all, we compute the k neighbors. Okay, say 20 neighbors, for example, we will find 20 neighbors of everyone. That one is this complex. So if there are total m data points and there are total n number of dimensions, so this is how much it is going to take time to find k nearest neighbors. So the total time is going to be really, really complex. Okay, so here the most horrible part is the m square one here, because m is number of instances, and if n goes really high, this will become impossible. No, generally we keep m as instances, n as features. Okay, all right. K cubed. Why k cubed? Because if you think about this weight optimization here, so basically this is not m, actually this is k. Okay, it's going to go over k. So what it is doing in this case in the weight optimization, that for every individual dot on the plane, it's finding it has found there are k nearest neighbors, right? Then what it is trying to do is it's trying to express each of the k neighbors as the current data points, and this is what it's going to do for every element. So for every element, it's going to uh, find out big k nearest neighbors, and then operate on that. And that's why here it ends up doing multiple trips to the neighbors, and that's why it is k cube. Okay, all right. So basically what you see is first of all, we find the k neighbors of everybody. Then we do the weight optimization. We find the distances or weights between the neighbors and this, so that we can say that they are still holding hands, right? If that weights are maintained. And then we construct a low dimensional representation. We start moving all the data points uh, by individually removing the dimensions, some dimension, and then and retaining the same weights. Okay, so again, this is going to be really slow. So this is how we can unroll a twisted manifold. Okay, so All right. There is something called multi-dimensional scaling. Okay. So there's something called multi-dimensional scaling. So from Scikit-Learn manifold, we can import MDS and we can pass the number of component that we're looking for, and then it'll do the. These are other dimensionality techniques that you could use. And so using MDS, you could reduce the dimensions, then isomap. So let me just show you the previous steps. A question from Bintao is, what does O stands here? O stands for order of. Okay. So as we discussed earlier, the order of it means that that if we, let's say here, right, the time taken to find the k nearest neighbors is a function of m multiplied with n multiplied with log m multiplied with log k. So m log m into n log k. This is the time that it takes to find the k nearest neighbors. Okay. All right. So here LDA is a bit different. Okay. LDA is again a bit different. So MDS is another algorithm which is used for reducing dimensionality, and it trying to preserve the instances as much as it can. Then there is something called isomap. It creates a graph connecting each instances to its nearest neighbors, and then reduces the dimensionality. Okay. So it tries to preserve the geodesic distances between the instances, right? So again, there could be many ways we can express it. All right. So okay, so MDS is for manifold, then isomap. So isomap creates a map connecting each instance to its nearest neighbors, then it reduces dimensionality. So exactly the way we did in case of LLE, okay, we in the similar way, it also connects each instance to its nearest neighbors, and then it reduces the dimensionality. Okay, it tries to preserve the geodesic distances between the instances. And the third one is the t-distributed stochastic neighbor embedding. Okay. Again, it does the similar thing. It tries to keep the instances close and keep the dissimilar parts away, and that's how it reduces dimensionality. Mostly used for visualizing clusters in high dimensions. If you have high dimension spaces and you want to visualize clusters, you might want to use t-distributed stochastic neighbor embedding, TSNE. Okay. Now there is another technique called LDA. LDA is a classification algorithm. During training, learns the most discriminative accesses between the classes. Okay, so it basically is a classification algorithm, and while we are training this algorithm, it learns the most discriminative access between the classes. Okay, so basically it tries to find the access which is discriminating the various instances the most, and accesses can be used to define the hyperplane to project the data. Okay, I think this is supposed to be hyperplane to project the data, and projections will keep the classes as far apart as possible, and a good technique to reduce dimensionality before running classification algorithms such as SVM classifier. Okay, so these are the few more algorithms, so you could try them out. So here, this is how we use MDS. Okay, As in, do you mean to say that it's a classification algorithm? Do you mean Noor's question is the first point and last point not contradictory in this slide, or? Okay, so here it means that before trying out moving on to SVM classifier, you could try LDA. Okay, it essentially means that. Okay, or sorry. So it's a good technique to reduce dimensionality before running classification algorithm. So basically, you could actually reduce the dimensions. Why we are saying SVM classifier? Because remember when we were doing SVM, the SVM actually, if the number of dimensions are more, SVM becomes really slow, right? So if we are planning to use SVM classifier, we might want to reduce the dimensionality, and LDA is a best choice for doing that. So we'll use it for reducing the dimension. A question from Gopi, I would say that it is not a classification algorithm, but a pre-processing technique useful for classifying, right? So I would say in this way that LDA is basically helps us figuring out those accesses which differentiate or discriminates discriminate the training set. So the accesses which divide the data, that's how it is. And okay, so this is where we are. So this is, let's say there is a manifold. We are using MDS to do manifold. And then here, then we are plotting. Okay, so here we are reducing the dimensions of the manifold and trying to present those. Okay, all right. So you can see that the one that has actually unrolled our uh, our Swiss roll. I'm trying to avoid saying that. Okay, the one that has unrolled our manifold the best is probably the isomap, and then we have TSNE, which is also kind of unrolled it, but it is kind of not that smooth. Okay, so isomap is, yeah, has done a very good job here. All right, so that's pretty much with respect to the dimensionality reduction techniques. And so in general, when the data set is not too twisted, then we can use KPCA, we can use PCA. If the data set is really twisted, then we might have to use Kernel Pca, LDA, or isomap, or LLE, or MDS. So we might have to try out these before, if our data set is really twisted. Keep in mind that most of these algorithms which are for non-linear or twisted data set, they are actually horrible when it comes to performances. Okay, because they take a lot of time. Even finding the nearest neighbor is a complex process, and on top of it, uh, keeping the neighbor relationship is a hard part. So isomap does the same thing, keeping the neighbor relationship intact. Similarly, the MDS also does try to do the same thing, keeping the nearest neighbor relationship as near as possible, and so on. Okay, so that's the summary. Okay. Kamal's question is, we use dimensional reduction only for testing and training time. Otherwise, we should avoid it. So there were three purposes. Okay, let me just summarize why dimensionality reduction. Okay, why dimensionality reduction? One, the the number of dimensions. Okay, so let me put it the other way. So number of dimensions are a problem. One is algorithms don't give good results, right? Like for example, in case of manifolds, okay, the accuracy is really bad. And the second is the time taken goes really high. Time taken goes really high or impossible, you can say, in many cases. Now, third is the memory it consumes. Memory consumed by so many dimensions is really high. Okay. Fourth is the this okay. So so one is algorithms don't give good results on higher dimensions. Second is the time it takes. I think this would be the third, not second. Okay. This would be the third, not second. Okay, so the memory consumed by so many dimensions is really high, which means it doesn't, the main algorithms may not work because you remember in case of NumPy, we basically give the whole matrix to most of the algorithms, and the matrix, even if some of the values are empty, still it's going to consume a lot of memory, right? And then time taken is really high. Okay, in many cases. So in a lot of cases, it makes sense to do the dimension reduction. Okay. Okay. Think about remember, yeah. So a question from Kamal is: I agree to second and third, but suppose if memory and time is not constrained, but should we still do it for one? Correct. So think about this way, that the let's say we are doing some kind of classification of the data at manifold, right? In case of twisted data set, right? Then most of the algorithms will not be able to perform well. They won't be able to fit a plane, they won't be able to fit a twisted plane, and it's going to be really, really difficult, correct? Therefore, it's better to unroll manifold and then get the results. And same is true for other things as well. So in the multi dimensions, as we talked about earlier, let's say we are trying to fit a linear plane, right? Since the data is sparse, okay, okay, let me just put here for two reasons here. One is sparse data, sparse data, and other is manifolds, manifolds, etc. Okay, so those are the things. All right. So since the sparse is data, the data is sparse, it's a very important discussion we must have. So why we are doing dimensional reduction is, one, algorithms would give better results. Okay. If our data is having lower dimensions, reason is if the data is sparse on certain dimension, the approximation is generally wrong in case of if algorithm is trying to fit the data. Other is if the data is in the form of manifold and twisted, then you can't really apply any of the algorithms that we have learned earlier for classification or regression. Okay, so that's why Sometimes when the data is complex, we could basically unroll the data or make the data less sparse by reducing the dimensions, and thus the algorithms would give better results. So, all right. So as an experiment, yes, upfront we do not know what kind of data it is, right? So let's say you experimented with data and you realize that all of your algorithms have given you s- really bad performance. Okay, all of the algorithms are giving really bad performance. At that point of time, it would be worthwhile to take a look at data and check if the data has manifolds or data is what kind of data it is. And once you take a look at that, then once if you see that there is manifold, then you can try to unroll it using either of the techniques. Or even if you don't know whether there are manifolds or not, you could just give it a shot and take a look at whether it improved the performance or not. Okay. So question from Kamal is, so are you suggesting that we always try to do all kinds of dimensionality reduction other than using all other algos and kernel tricks to check which gives the best fit? Yes. So I think the best way would be to just have this as one of the items in the pipeline. And in case your algorithms are performing bad, okay, then consider this as an option. So yes, it's kind of a pre-processing technique in your toolkit when necessary. Okay, good. I think that's a good way to put it, Gopi. All right, so that's pretty much. In the next session, we will try to see if we can cover these parts. Okay, we will go over the brief topic of 4-bike and then XGBoost, time series, name bias, and next Sunday we'll start the deep learning one. Sure, I'll commit it, Binta. Let me do it right away. Okay, before you can. All right. Okay, so all right. A question from Kamal is, but say in a competition there is nothing like achieved. You can always put efforts to make it better. Correct. Correct. Okay. If there are multiple people competing, then you can do that. Okay. All right. Thank you for letting me know. I'll just save this. Okay. Great. I have pushed this, and there are a few more questions. So basically, these are for improving the performances, and as in the idea of every algorithm is to have really 100% performance. So we tend to achieve that 100% performance by using all these techniques. A question from Noor is, if we are distorting the data set this much, then how does actual estimation, prediction, or classification happen? That is, if we twist a Swiss roll so much that it loses its characteristic or shape, then how the training model would classify the new instance given it as Swiss roll. Okay, so the thing is that we will also transform the training set equally and do the prediction using this. Okay. So we'll, whatever transformation that we are applying here, we will also apply the same transformation there, and then we'll do that, predict. Okay, both training and test, correct. Thank you, Gopi. I hope this session was useful. I look forward to see you next Saturday, Sunday. All right, so have a good lunch, and for some, have a good breakfast. All right, so bye-bye. Have a good day. I look forward to see you next week. Next week is exciting. We are going to start deep learning next week. All right. we are most likely go and straight away start our work with TensorFlow and do the hands-on on TensorFlow. Okay, bye-bye, have a good day. Thank you, everyone. Thank you for wonderful set of questions and keeping the discussion lively.